Today we're going to continue finding sums of geometric series. Last class we found the sum of a partial series, that was the sum of a certain number of terms, and today we are going to discover what happens when the series goes on forever. And sometimes we can find the sum of a series that never ends, sometimes we can't. So first thing we're going to do is look at this series right here and find the partial sums. And what I mean by that is the sum of the first term, if we just had one, would be just one term, 1/2, 0.5. The sum of the first two terms, if we add them together and we converted it to a decimal, would be 0.75, and we went on like that. We added the first three, and we did the math for you to the sum of the first five. Then we put them on this chart, and now what I'm going to do is I'm going to graph the term with the sum, and we're going to look at that relationship, and hopefully it will become a little more apparent on how we can add something that's never going to end. So 1 will go to 0.05. The sum of our first two terms will be 0.75, so 5, 6, 7, right here. Okay, first three will be about here. Sum of the first four and sum of the first five. And I'm already off one. That's okay, I can fix that. Okay, so now we can see how, if we keep going, it's like we're approaching a number. We may not get there, but we call that it's approaching a limiting value. So for this example, as n approaches infinity, that's as our terms go on and on forever, the output, which is the sum of our terms, will approach 1. So what that means, just in the regular way we would speak, this series is never going to end. It goes on and on and on. It's infinite. But we can still add up those terms, because if you think about them, these fractions are getting smaller and smaller. So we're going to keep adding them on, and this is going to approach 1, and we can see that from the graph. We can also find this algebraically with this formula, and in order to use it, we need to know the common ratio, that's R. And if I look at our original series, I can see to go from 1/2 to 1/4, we're multiplying times 1/2. From 1/4 times 1/2 is 1/8, and then I'll check one more just to make sure I'm not making any mistakes. So our common ratio is 1/2. So now I can use this formula to check my work as well, algebraically, and the sum of this infinite series will be my first term, which is 1/2, over 1 minus my common ratio, which is also 1/2. The second part of this, that's just a comma and telling you in order to use this formula, the absolute value of the common ratio has to be less than 1. And I'm going to let you think about that, why it has to be less than 1 to use this formula. When we do this, you're going to end up with 1 as your answer, the same way as we did when we graphed and we could see it was approaching that. Now we are going to try a few example problems using the same formula from the last page. It's typed out for you here, same exact thing, with a reminder that if your common ratio is greater than or equal to 1, the series has no sum. We cannot use this formula. And the reason for that, you are thinking about, rather than me just telling you. So looking at our first problem, A, I'm remembering that a sub 1, my first term, is 3. My common ratio is 1/4. Now I can apply the formula and substitute those values in, and the sum will be 3 divided by 1 minus 1/4. And then to simplify that, that will be 3 divided by 3/4. And then when I'm dividing by a fraction, I'm multiplying by the reciprocal. So that will be 3 divided by 4/3. The 3's cancel out, and my answer will be 4. For the next problem, we need to figure out our first term and our common ratio. And I can look and see our first term is going to be 1. And then for our common ratio, we need to think about what we're multiplying every time to get the next number. And just as a reminder, you can also determine these with division. So if I take -3/4 and divide by the term before it 1, I can figure out that will be -3/4. And you want to try more than 1 just to make sure you did this correctly. So 9/16 divided by -3/4 will give us 9/16 times 4 over -3. When we divide by a fraction, we multiply by the reciprocal. 1, 4, -1, 3, and we get -3/4. And if you check all of these, your common ratio will be -3/4. From here, we're going to use the same formula. And my sum of this infinite series will be 1 over 1 minus my common ratio, which is -3/4. So when I simplify that denominator, I'll have 1 over 1 plus 3/4, and then 1 over 7/4. And remember, to divide by a fraction, we're going to multiply by the reciprocal, so that will be 1 times 4 over 7, which is 4/7. Now we are going to find the sum, if a sum exists. So to do that, we need to know the first term and the common ratio. And a sum will exist if the absolute value of the common ratio is less than 1. So really, we need to determine the common ratio and see if it's less than 1. So I can do that by figuring out what I need to multiply every time, or the opposite of multiplication is division. So if I take my second term and divide it by the first term, -3 divided by 1, that will be able to determine the common ratio. And now 9 divided by -3 will be -3. I'm testing them all to make sure I didn't make a mistake. And then -27 divided by 9 is also -3. So -3 is my common ratio. And then I can think that the absolute value of -3 is a +3. 3 is greater than 1. So because 3 is greater than 1, we cannot find the sum. There is not one for this. So the answer is no sum, and the reason is because the absolute value of the common ratio is greater than 1. Okay, the next example. First thing we need to do is, we can see the first term is 1. I need to find that common ratio, and I'm going to do that the same method I did before. 3/2 divided by 1 is 3/2. So now I'm thinking my common ratio is 3/2. I want to test another one just to make sure. 9/4 divided by 3/2 will be 9/4 times 2/3. So that's 4, 1. I'm canceling. And now I have 3/2. So now to test for my last term, 9 times 3 is 27. 4 times 2 is 8. My common ratio is 3/2. And then 3/2 is greater than 1. So this also does not have a sum because my common ratio is greater than 1. Now we have a pendulum, and we want to figure out the total distance it travels if every time it swings, it only goes 80% of the swing before it. So if we're not sure where to start, we can label our diagram or a picture and try to write something down. I always say draw something if you don't know where to begin. So I'm going to look at this entire first distance and say that's 18 inches because they give us that. We're going to start with the first swing being 18 inches. And then it says our second swing is going to be 80% of the first swing because it's getting smaller every time. So 18 inches times 80%, so that's 0.8, will give us our distance for the second swing, and that's 14.4. I just put that in on a calculator. So right now we have 18 plus 14.4. And let's see for the third swing what we do. It's going to be 80% of that. And 14.4 times 0.8, I have 11.52. 11.52. So it's getting smaller, but this is going to go on and on and on and on. And we can see it's going to take a while. But we've already figured out that our first term is 18. And what I'm doing every single time is multiplying. So our common ratio is 0.8 because I knew I had to change that to a decimal for 80%. And this pendulum, it's going to keep going. It didn't say add up after 10 swings or 50 swings. We're just going to keep adding up forever, and my common ratio is less than 1. So I can apply this to my formula for an infinite geometric series. And I can see my first term is 18. I'm going to have 1 minus my common ratio, which is 0.8. And this will give me my total distance. And I'm going to put all of that in on the calculator. I have 18 over 0.2. And that will give me 90 inches. Here are 6 practice problems. Please pause the video, try the practice problems, and then when you resume, all the answers will appear. Here are the solutions to the problems. Please check your work, see your teacher with questions, and also check Schoology for your homework assignments.